My name is Leong Cheng. I am a PhD candidate at HKUST, and now I will present our work, Optimizing Image Compression via Joint Learning with Denoising. Our source code is available on GitHub. DSLR cameras are usually equipped with large and fast lens, plus excellent sensors to take high-quality images. However, people tend to use smartphone cameras for convenience, where high levels of undesired noise usually exist in the captured images due to the small lens and sensors. Usually, we need to compress the images before storage and transmission. However, without the capacity to tell the difference between image details and noise, general image compression methods allocate additional bits to explicitly store the image noise during compression. A natural and straightforward solution is to go through a sequential pipeline of individual denoising and compression methods. However, a simple combination of separate models can be suboptimal due to additional time overhead and accumulation of errors. In this paper, we propose to optimize the compression algorithm to be noise-aware as joint image, denoising, and compression. This is an overview of our proposed framework for the joint task. Our framework is built based on a pre-trained image compression model, where it contains a pair of analysis and synthesis transforms, a hyperprior for capturing spatial redundancy of the latent code, and entropy models plus a context model for bit rate estimation. To fine-tune an image compression model to be noise-aware, we introduce a two-branch design. The guidance branch takes clean images as input, and the denoising branch shares the same parameters as the guidance branch with plug-in features denoisers and takes the noisy images as input. Note that the guidance branch is disabled as we do not have any information of clean images during inference time. We validate our joint framework on synthetic Kodak and CLIC images and a real-world dataset SIDD. Results show that our method gains a significant improvement over the existing sequential and baseline methods in terms of rate distortion, generalization capacity, and decoding speed. We add synthetic image noise to images in raw space according to a two-parameter signal-dependent Gaussian. During training, the short and read parameters are randomly sampled. During testing, we choose 4 predetermined parameter pairs at gain 1, 2, 4, and 8. This is the comparison of the overall rate distortion performance on the synthetic Kodak images. We can see that our RD curve in blue is much better than the sequential and joint baselines. We can observe similar results on the synthetic CLIC images. If we break down the overall performance at individual levels, we can see that our joint method can better generalize to the unseen noise level 4 with gain 8 noise. Here we show some visualization results on our synthetic Kodak images. We can see that our solution has a better capacity to restore structural texture and edges. Here are some more visual results for the synthetic CLIC images. We also validate our joint method on the real-world SIDD, and our method outperforms all the baseline solutions. Some visual results on SIDD. We can see that the texts in our results are much clearer at even slightly lower bitrate. For more details of our results and implementations, please refer to our paper and GitHub. Thanks for listening.